Okay, so here's our second example for section 4.3, and this one's a nice one to look at because, yeah, the derivative takes a little bit more work. Critical points are going to take a little more work, so it's a good one for us to look at. So we are going to consider the function f of x equals x to the 4/5 times x minus 4 squared. And again, kind of same instructions as before on what open intervals is the function increasing and decreasing, and then we're going to find the local extreme values, maximum and minimum, if the function has those, and we'll say where they occur. So cool. First things first, we need the derivative of this. So let's do f prime of x. And this is definitely going to be a product rule situation because we have one function multiplying another, x to the 4/5 times x minus 4 squared. I guess you could distribute everything out maybe and use the power rule, but let's practice our product rule here. So we'll go our first function times the derivative of the second. Derivative of x minus 4 squared, and then plus our second function times the derivative of the first. Okay, so we'll have x to the 4/5 times, that would be 2 x minus 4 to the first power. And then just seeing if there's anything with the chain rule there, times the derivative of that inside would just be times 1. So we don't really need to show that. Multiplying by 1 isn't going to change anything. So we're just going to have 2 times x minus 4 for that derivative. And then we'll have our x minus 4 squared here. And then power rule for derivative of x to the 4/5. That would be 4/5 and then x to the 4/5 minus 1. So 4/5 minus 5/5 would give us negative 1/5. Okay, there we go. Let's clean this up a little bit here. We'll have 2x to the 4/5 x minus 4 plus 4/5 x to the negative 1/5 x minus 4 squared. Okay, so that right there is actually our derivative, but it is going to be rather difficult to find the critical points from this form of the function. It's a bit of a challenge. So if we do a little bit of factoring here, we can really get this into a better form that's going to help us out with the critical points and kind of everything after that as well. So yeah, this is a good process to know how to do. It can really, it takes some work up front, but it can save you some work later on in the problem. So let's factor out the lowest powers of the factors that we have here. So we have some factors of x minus 4. So taking out the lowest power of that would be taking out x minus 4 to the first power. Factor out x minus 4. And also our lowest power of x, which we have x to the 4/5 and x to the negative 1/5. So this is going to win. That's going to be our lowest power there. X to the negative 1/5. I'll just make a little note why we chose those particularly. Lowest power of all your factors. Okay. And let me write that out front here. Take out x to the negative 1/5 and x minus 4. All right, and then we'll have to see what is left over. So if you're a little little maybe dodgy sometimes on taking out more complicated factors like this. The trick is to take your original term. So for this first original term, that would be 2x to the 4/5 times x minus 4. And then we're going to divide that by whatever we just factored out. And that'll give us whatever is remaining. So if we divide by x to the negative 1/5 x minus 4, the things we just factored out, that will show us that the x minus 4's cancel. And then 2x to the 4/5 over x to the negative 1/5. Well, when you divide your exponents or your exponential terms with a common base, okay, you would subtract these exponents, right? Rules of exponents, good stuff. And so that would be 2x to the 4/5 minus negative 1/5. And so that would give you 5/5 there, which is just 1. So we end up just getting 2x for our remaining term there. 2x. Okay, so yeah, this is a little in-depth on the factoring, but sometimes I really think it's worth it. Same thing for your second term now. You would take that second term, 4/5 x to the negative 1/5 x minus 4 squared, and then divide by what we just factored out, x to the negative 1/5 times x minus 4. Okay. And then you'd see that one of your x minus 4's cancels out, and the whole x to the negative 1/5 thing is gone. That's kind of nice. So you have 4/5 times x minus 4. Okay, so that would be our second remaining term. All right. Phew. Okay, so there's your factoring. And now let's see what we've got, because we could do a little bit more simplification here. If we distribute our 4/5, okay, you'd have 2x plus 4/5 x minus 16/5 inside there. And keep dragging everything along here. Okay, 2x, that would be 10/5 x plus another 4/5 x. That would give us 14/5 x. And then minus 16/5. And then even inside of there, you could factor a little something out as well, just to make it look a little nicer, a little less fractions going on. This step is optional, totally. I mean, at this stage, you could really work with this derivative, but I'm going to factor out, looks like 2/5 would be a good choice. Okay. Because that, if we bring out a 2/5, that would leave us with just 7x here. All right, take out 2/5 from that, and then taking out 2/5 here would leave us with minus 8. So then we got some nice whole numbers to work with. Okay. Then just to finish it off for prettying this up a bit, I'm going to stick it into a rational form. So on top, we'd have our 2, our x minus 4, and our 7x minus 8. Those would go up in the numerator. Then down in the denominator, we would have our 5, and then x to the negative 1/5. That would become positive 1/5 down in the denominator. So here we go. Just like that. Shoo. Okay. So that is, again, our first derivative, which we really had the first derivative back at this step. We had actually taken all the derivatives we needed. All of this is really just cleanup to get it into a nicer and more usable form. So it does take some doing here, but it can help us. Because yeah, now when we want our critical points, we're looking for where f prime of x is undefined and where it's equal to 0. And this lets us see that, oh yeah, there is actually going to be a point where this function is undefined. All right, if that denominator equals 0. So getting it into that form where you can see the denominator, that actually helps us out here. Because we can just kind of snag that denominator, 5x to the 1/5, and see where that equals 0. And that would be at x equals 0. So we do have an undefined spot. And then for seeing where the derivative itself equals 0, that would be like setting this whole fraction equal to 0. You could multiply on both sides by x to the 1/5. Basically, all you need to do is see where the numerator equals 0 here. So 2 times x minus 4, 7x minus 8. See where that equals 0? We would come up with x equals 4 from that first factor. And then from the 7x minus 8 equals 0, that would be x equals 8 divided by 7, 8/7. Phew. Okay, so those are our critical points. Wow. Okay, so we have 3 critical points here, 0, 4, and 8/7. Okay. But this question was not just asking for the critical points. We now have to look for where the function is increasing, decreasing, and then its local maximum and minimum values. So we are going to set up, like we did in the last problem, a number line to test our first derivative. Okay. So testing, 1, 2, 3. Okay, testing f prime of x. Okay, set up a number line here. To test the first derivative. Okay, and I do recommend writing the fact that you are testing f prime of x here on this number line, because later on in this chapter, I think actually just in the very next section, we're also going to be testing the second derivative. So you don't want to mix your number lines up because they do different things and they affect different things. So that's why it's nice to label them. So we're using our first derivative here. I'm just going to put our function there as well. Okay, for the first derivative, that is. 5, x to the 1/5 would be the 5th root of x. Okay, so we know what we're looking at. All right, so now let's put our critical points on the number line here. We have 0, we have 8/7, and we have 4. And I know that's not to scale. There's, the spacing here is a little weird. What you're really trying to get from this number line is just being able to see the different intervals. So it'll work. You don't have to be super precise on your number line. We know at 2 of those critical points, at 4 and at 8/7, that those were where the derivative actually equaled 0. So let's kind of label that. And then here at 0, that was where the derivative was undefined. So I'm just going to make myself a little note of that by putting a u up above it. Okay. And yeah, now we need to test our first derivative. So we have 4 different intervals to try out here. Okay, 1, 2, 3, and 4. And you can pick values in each one of those and kind of picture what would be going on. And I do want to show you guys a shortcut for this because especially with having the first derivative function that we do, plugging in a bunch of different values and finding the actual value of the first derivative can sometimes take a little more time than you really want to spend. When all we're trying to do here is figure out if the derivative is positive or negative, there's a shortcut for this. Okay, and it's called sign analysis. Okay, so sign analysis is a shortcut. And basically the idea here is when you are plugging in, and I'm saying that in quotes, plugging in your test value, you're not going to actually find the number. You're just going to determine whether each factor in this derivative function is positive or negative. Okay. So, for instance, let me show you what I mean here. Let's pick a test value in this interval from 0 to 8/7. I'm going to choose to test x equals 1. But you could pick, you know, anything you can think of in that interval. Okay. And instead of plugging in 1 itself into all these factors, I'm just going to say, okay, is it positive or is it negative? And looking in the numerator, the first factor that we have is a 2, and that's a positive 2. So the first thing on top is positive. Okay. Now our second factor up in the numerator, x minus 4, if x equals 1, okay, 1 minus 4, that would be negative 3. But instead of putting negative 3, I'm just going to make a note that that factor is negative. Okay. You move on to the next factor. Okay, up in the numerator, that's your 7x minus 8. Okay, if x is 1, that would be 7 minus 8. Okay, negative 1. But instead of writing negative 1, I'm just going to make a note that that factor is negative. So up on the top, we have a positive times a negative times another negative. And then down in the denominator, we have 2 factors here. We have a 5. That's a positive 5. So I'm going to make note of that. And then we have the 5th root of x. And the 5th root of 1 is just 1, so that one's nice and convenient to actually calculate. But if you were plugging in something else, like, you know, if you hadn't chosen 1 here, maybe if you chose 1/2 or something like that, the 5th root of 1/2 would be a much more challenging numerical value, but it would still be positive, and that's all we really care about. So I'm just going to make a note that that factor is positive. Okay, so we have here a positive times a negative times another negative. So is this numerator here ultimately going to be positive or negative? What do you guys think? Yeah, okay, good. Got a plus in the chat there. Very good. So this is positive because the 2 negatives make a positive and then times another positive. Yay. Okay, so we have a positive numerator and also a positive denominator. And so that tells us that the whole thing overall is going to be a positive first derivative there. So even though we didn't find the actual number for the f prime of 1, we found out that it was a positive number, and that's all we needed to test, really. Okay, so let's do another one here. Let's do maybe something between 8/7 and 4. Okay, so you can pick whatever value you want in your head there, maybe like 2 or 3 or, you know, whatever. I'm gonna personally, I think about x equals 2, but it really doesn't matter. We're just trying to figure out, again, whether each factor in our derivative is positive or negative. So f prime of 2 or 3 or whatever you're thinking of. All right, go through your factors. The 2 is still positive. That one's kind of given. Okay. And then think about your number minus 4. Okay, so for me, I chose to think about x equals 2. 2 minus 4 would be negative. If you chose like x equals 3, 3 minus 4 would also be negative. So we're on the same page there. You got a negative second factor. And then for the third factor, okay, 7 times your x value of choice in there, minus 8. Mine would be 7 times 2 minus 8. That would be positive for me. And whatever you chose, it should be positive as well. So positive factor. Boop. Okay, and we look at the denominator then. The 5 is still positive. That's another kind of gimme there. And then think about the fifth root of your number. Fifth root of 2, fifth root of 3. Yeah, they would be some weird decimal values, not very conducive to calculating. But what really matters is that they would both be positive values. Fifth root of 2 or the fifth root of 3 or the fifth root of whatever you're thinking of. It's going to be positive in that interval. So yeah, we end up having here up in the numerator, positive, negative, positive. That would be negative overall. And then a positive denominator. And if you have a positive divided by a negative, that gives you a negative result. Okay, so the first derivative in that entire interval is going to be negative. So again, we didn't find the value for the first derivative. We just found the sign of it, the fact that it's negative, because that's what we need. All right, lets us be a little more efficient. So you would do the same type of thing in your outer intervals here. Let's see, you might test like x equals 5 or anything bigger than 4 over in that far right-hand side interval. You'd end up having factors that are positive, positive. Okay, 7x minus 8 would also be positive. Okay, and then your denominator is actually all positive as well. 5 is positive. Fifth root of anything bigger than 4, still positive. So all those positives make for a positive first derivative there. And then over here, values that are less than 0, you just want to think about any negative number, anything whatsoever there. Okay, and you're going to test your factors again. So numerator, still got the positive 2. Okay, next factor, x minus 4. Well, any negative number minus 4 is still going to be negative, just more negative. Okay. Same thing with 7x minus 8. No matter what negative number you're thinking of, that's still going to give you a negative result. So we got positive, negative, negative up in the numerator. And then down in the denominator, the 5 is positive. And then the fifth root of a negative number, any negative number, is that positive or negative there? Just for this bit. Let's think about our fifth roots. Yeah, there we go. Got it in the chat. It is negative. Nice. So good. We have a positive and a negative factor in the denominator. So this gives us, okay, two negatives and a positive up top. That's positive overall. And then we're going to divide by a negative. And so positive over negative gives us a negative result for that interval. All right. So that's how you do this sign analysis stuff. I'm a big fan of that because it saves you time when you don't have to calculate the full values of everything. Because now we can see, just based on our signs, plus or minus, where our function is going to be increasing and decreasing. We've got some increasing intervals here, increasing there. All right, increase with the positives. And then with our negatives, we got some decreasing intervals here and here. And so, yeah, that'll help us answer the first part of this question. Increasing intervals are going to be the interval from 0 to 8/7, and also the interval from 4 off to infinity. Okay, so there's our increase, and then decreasing intervals are going to be the other ones. That's our interval from -infinity up to 0. And our interval here in the middle, 8/7 to 4. Okay, cool. So that's good. Let's see now. We've got our increasing and decreasing, and then we want to use our first derivative test and identify our extreme values, say where they occur. So we're looking for local maximum and minimum here, and we can see based on our little chart here where it's going to switch from decreasing to increasing, or the value of the derivative changes from negative to positive or positive to negative. Remember that we're going to get our local maximums where we switch from increasing to decreasing, okay? Positive to negative for the max. So there's only one spot where that happens on this chart here. Increasing to decreasing, positive to negative. This is going to be our local max right there at 8/7. Oop. Trying to erase that highlighter. There we go. Okay. So we would say there's a local max at f of 8/7. And remember, when you're getting the value of this, the local maximum value of the function, that really is the original functions. Don't plug back into the derivative. And the value for this is not going to be pretty because you're going to have to plug back into this thing with 8/7. So you've got to take like 8/7 to the 4/5 power and stuff. It's not going to be great. So if I want a specific number of decimal places, I'll tell you. I think my math lab should tell you as well if they want a specific number of decimal places. And if you're ever in doubt, just ask. So if you plug 8/7 in here, you get something around 9.1-ish. So we'll go with that. All right, approximately 9.1. And then for your local minimum values, that's where we would be switching from a decrease in the function to an increase. So your first derivative goes from negative to positive. And since we had a couple different critical points here, there's actually 2 critical points where that happens. One is at 0 right here, decrease to increase. And then the other one is at 4. You got that same thing, decrease to increase there. So we're going to have 2 local minimum values. And we label both of them as local minimums because you'll notice that's not like an absolute minimum or anything, just local. So we just want to see what the values of each one of those are. So one is going to be at 0 and one is going to be at 4. And so we would plug those values back into the original function. Okay, and thankfully with f of 0, you have 0 to the 4/5 and then 0 minus 4 squared. Well, that is all just going to equal 0 actually because of this factor. So that's kind of nice. And then a similarly nice thing happens with f of 4. Sure, you've got 4 to the 4/5, which is messy, but your second factor becomes 4 minus 4 getting squared, which is 0. So f of 4 is just 0. Well, that's nice. All right. So both of those happen to equal 0. And that really is just kind of a coincidence that they ended up having the same value. That's not guaranteed that both your local minimums will have the same y value. It's just a nice thing that happened with this particular problem. So there we go. There is our increasing, decreasing, local maximum, local minimum. Kind of to finish it off here, let me see if I can get OneNote here to graph the function for us. That way we can verify this and make sure that it makes sense with what we found. So let's see. Oops, that is not what I wanted. That is what I wanted. Okay, can we select that? Nope. Okay, let's see. Maybe if I write it, x to the 4/5, x minus 4 squared, maybe it'll like that better. Math? No, it didn't really like that. Let's see. Well, maybe I'll just need to put in a graph later on. Let's see if I can get this to work. 4/5. Or maybe it'll like it better if I write it as a 5th root of x to the 4th power. Maybe they'll like the 4s better like this. Okay, let's try that. All right. Yeah, it did like that. Okay, 5th root of x to the 4th, x minus 4 squared. Okay, cool. Yeah, there's a graph. All right. So that is what our function looks like. Cool. Let's drag it down here so we can see it next to our whole increase decrease thing. Okay. And so, whoops, get the keyboard out of the way. If you look at what we got here, we were saying that the function is decreasing first on this interval here from -infinity to 0. And you can see on the graph that that's actually true. The function is decreasing down to 0 there. And then we had said it was going to increase from 0 to 8/7. So you can see it's starting to increase, 0. And then this up here at the top, that critical point there, that's got to be where 8/7 is. And you can see it's just past 1 on the x-axis. So there's our 8/7 that we were looking at. Nice. And then we can see the decrease happening again. Values are decreasing until we get to our other critical point. And you can see that on the x-axis real clear is at 4, just like we said. So nice. And then we had said it was going to increase again from x equals 4 to infinity, and it does. Sweet. So our increase-decrease intervals were spot on. It's really nice there. You can also see our local maximum, f of 8/7 equals about 9.1. And let's see, yeah, there's 5 on the y-axis, 6, 7, 8, 9. Yep, that mark is just above y equals 9. So there's our local maximum. Perfect. And then for our local minimums, we have f of 0 equals 0 right here, and f of 4 equals 0 right there. And you can see that, yeah, those are actually local minimums. They're the lowest thing in their little area, and the y value really is 0. So cool, we nailed it. You can also see, again, the critical points even, how we noticed that the derivative was 0 at 8/7 and 4. You can see that reflected in the graph right here, 8/7 and 4. Those both have nice horizontal tangent lines. Okay, so the derivative really is 0. And then at x equals 0, we have a sharp, sharp corner. In fact, I think that would even, that would be called a cusp there. So the derivative is undefined at that point. And that is exactly what we had found. That was how we came up with that critical point in the first place. So it all ties together and it all goes with the graph of the function. So it's pretty cool.